charge of the...
Okay, so let's start with number 56. Pop, can I have my book back, or do you still need it?
No, I'll give it back. That's my bad.
Oh, we're good.
It's on the right page for you.
Oh, even better. Score for the home team. Okay. So on number 56, it's an interesting idea. So you got a pollen grain like such, and it's got the diameter. Pay attention to the fact that this is the diameter. Okay? Typically, the reason that you're given the diameter is because that's easier to measure than the radius. Okay? You have a lot of times you use a measuring device called a caliper. And a caliper is the set of jaws that you can open and close. And so it's very difficult to sit there and go, well, how do I measure from the center of the pollen grain to the outside? But if you have a set of calipers, which are like little jaws, then it's very easy to measure the diameter. Oh, you measure the diameter, you divide that by 2, boom, there's radius. So at the end of the day on 53, you got to find the volume, and that's going to be that 4/3 pi r cubed. And if you need that for the test, I will give that to you. Don't worry about that. So then you can find the volume. And then from there you can find the mass. From the mass you can figure out the number of total amount of charge on that. So that total amount of charge based upon all of those electrons should be like about 0.06. Okay? So that's the total charge once you take the grams, which should be something times 10 to the negative 6 grams, and then convert that into moles, convert the moles into atoms by multiplying by Avogadro's number, then multiply that by 6, and then multiply that by the charge on each one, which is 1.60 times 10 to the negative 19th, right, Louis? So that will get you the total charge. Then, to calculate that force, then compare this with the weight of an earth, which is density of carbon. Okay, so you've got all the numbers. So here's the story. So then you're going to go F equals K Q1 Q2 over D squared. And you know how far apart they are. You know the charge on each one. You can calculate that force. And that force should be something times 10 to the 7th. Okay? Which is, now these, not very far apart. Okay? So if you look at this, right, they're 1 meter apart, about like yay. And so it's an interesting concept because the whole idea of why I assigned this is like, okay, if you could look at this in terms of all of that charge being at one point, if it was just the negative charge, and all of that negative charge on another part, separated by that would be like 10 to the 7th. Now, an aircraft carrier weighs approximately 9 times 10 to the 8th. So if you do this, if you take that force, the repulsive force, if it was basically saying, if you had all those electrons at one point and all those electrons at another, 1 meter apart, and you divide this, you get an answer of about 1/30. So the whole idea being is that, okay, you have an aircraft carrier. It's massive, okay? It's massive. It's huge. But if you could take two very, 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 very small pollens of grain, and they're even separated by 1 meter, okay? This isn't like these are like side by side. These are still separated by a distance of 1 meter. So if you could have all of that negative charge, and all of that negative charge, basically you're pointing at it as 2 points of charge. That, on those 2 pollens of grain, would be about 1/30 the weight of the force of an entire aircraft carrier. And so that's why I assigned that problem. Like, wow, okay? Now, obviously, those pollen grains aren't going to repel like that. Why not?
Because they have protons.
Yeah, they also have protons that are balancing out, okay? But if you could consolidate all of that negative charge into each of those 2 points, that repulsive force would be a staggeringly large number. Now, when you get to question number 60,
Do you want us to leave that in a fraction even if it's not like 1/30? Even if it's like a little different?
yeah, or if you can put it as, I guess if you can put it as a percentage, I put it as a fraction.
Okay.
If you want to put it as a percentage, that's cool too. Okay? I just had it as a fraction. Okay, so let's talk about number 60. So what happens here is that you're going to have two plates, and this is what's known as a parallel plate capacitor. So let me and we're going to spend a lot more time talking about capacitors. But what capacitors do is that they store up energy. So the first thing I want to do is I'm just going to hook this up directly to an LED light. And LED lights are cool because they don't take much energy to run. Okay, so here I've got your basic LED light. And what I have here is a hand crank generator. So, kind of like these electrons aren't going to flow unless you force them. Now, LED lights only light up if the electricity flows in a particular direction. So if I turn this in one direction, I can make the light come on. If I turn it in the opposite direction, nothing happens. Because LED lights are mono-directional. They only work if the electricity is flowing in one direction. So if I go like this, I crank it up. So am I doing work when I turn the handle?
Yes.
Yes, okay? And when I do work, I am creating electricity. I am exciting these electrons. And those electrons are looking for a path to go, and so those electrons are flowing through there, boom, light comes on. I stop, the light goes off. So it only goes when this is cranking. But when I crank it, I can make the light come on. So what I'm going to do next is I'm going to disconnect this system. And I'm going to hook it up to a capacitor. So capacitors, we'll spend a lot more time talking about capacitors. So the short version of capacitors is that they act like a dam on a river system, okay? And they store energy. So obviously if you're going to store energy behind water behind a dam, you have to build that water up. And so then if you want to release that energy, you open up the floodgates, the water flows out. So what I'm going to do is I'm going to crank this up, and I'm going to store electricity in the capacitor. So to do that, I have to create an electric field. So basically, this capacitor right now is neutral. So what I'm going to do is I'm going to induce an electric field. I'm going to make one side of this be positively charged, and the other side be negatively charged. So I'm going to crank this up, okay? And so what I'm doing is I'm creating an electric field. So now, if I let go of this handle, notice that that will unwind. So, because what it's doing is that it's offloading that energy. But if I crank it up and then stop it, and now I let go, now I disconnect it. So what I've done now is that I've stored electricity in here. So this is what's happening on question number 60. I have two plates. One's positively charged, one's negatively charged. But they're not going to get positively and negatively charged unless I do work to it. So then what I'm going to do is I'm going to take this, I'm going to hook this up, and again, this only flows in one direction, so I got a 50-50 shot of guessing right. Oh, come on, stay up there. So I hook this up. Strong. Then what you'll see is that LED light comes on. So what capacitors do is they kind of act like batteries. So I cranked that up, I stored a bunch of electricity because I created a positive and negative charge within that capacitor. So what I did is, if you go with the dam analogy, is that I stored a bunch of water behind the dam. And what I'm doing is that I'm allowing that electricity, that stored potential energy, to flow out, and that's lighting up that LED light. So this is what allows you, but there's a limited amount. It's going to go out here before too long. But the capacitors work great, for example, in your phones. Okay, hey, you want to take a picture at night. You need a flash, okay? Well, what happens is that the light on your phone that will allow you to have that flash is hooked up to a capacitor. So that capacitor is acting like a dam, and it stored all that energy. And capacitors, you can regulate how quickly that energy flows out based upon basically how big do you open up the floodgates. You open them up a little bit, do you open them up all at once? So if you want a flash from your phone, you want that energy to flow out very quickly because you want, bam, that flash of light, okay? And so that's going to drive which type of capacitor that you use. And so that's actually one idea that they're looking at for energy storage, is because it's cheaper to build capacitors than it is to charge batteries. Because literally, if you look at what's happening on number 60, this is, I can do this, I don't have to have like the ions and stuff like that. All you have to have is the plates. But if you can regulate the offlow of that energy, then you can figure out, okay, how much energy is that going to offload? So we hook them up to solar panels, we store that energy during the day, we offload that energy at night, boom, we use that to run our lights in the evening. So capacitors and battery work the same way. They're both going to end up storing energy. So on number 60, and if you need this particular equation, I will give this to you on the test. Okay? It's epsilon naught, which is the vacuum permittivity constant over area. So Q is going to be the charge on the plates. So what I just did when I cranked that up, I separated those charges because Mother Nature doesn't like those charges to be separated. Mother Nature likes, oh, hey, I just want to chill out. Can't everybody be in a state of equilibrium? So if I want to get that out of a state of equilibrium, I have to do work to it. So by me cranking that handle and separating and creating a positively and negatively charged plate, that's analogous to me lifting up this ball, okay? So the ball isn't going to jump up in the air on its own. I've got to do work to it. So if I want to charge a capacitor, I have to do work. I have to exert some force over a distance, whether I hook it up to a wall, battery, something. I have to have some source of energy to separate these charges. So what's happening here is that you've got a certain distance between them, and on this one you're told that it's charged to 10 nanocoulombs, so you have that value of A. Epsilon naught is, it's a number, it's on the back of that yellow sheet, okay, and it has some weird jacked up units, but it works. And then this is going to be the area. So if you crunch all those numbers right, you're going to get an electric field of 3.6 times 10 to the 6th newtons per coulomb. Okay, so that's the value of the electric field that exists between these plates. Okay, you got a positively charged, you got a negatively charged. Now, so this is one of the things that you should be able to do. Let's say that I tell you that the top plate is positively charged and the bottom plate is negatively charged. Okay? Now, if I just gave you that and nothing else, what's the direction of the electric field within that parallel plate capacitor? Is the electric field pointing up or is the electric field pointing down?
Down.
Why down?
Because of the positive test charge will be attracted to the negative and pushed away from the positive.
Yeah, so if I put a positive test charge here, it's going to do two things. It's going to be repelled by the positive plate and it's going to be pushed towards the negative plate. So the direction of this electric field is pointing downward, okay? So on the test tomorrow, make sure that in a situation like this, you can figure out the direction of the field. Because if you can't figure out the direction of the field, you don't know what particle is going to do within that. So make sure you can figure out the direction of the field in a situation like this. Okay. So then you want to calculate the force, and you're just going to use Eck. So now you know the value of the field. Now, the Q is going to be the charge of the particle in the field. So in this is a proton, right? Okay. So that's going to be 1.6 times 10 to the negative 19th coulombs. So look what happens to the units. You have newtons per coulomb multiplied by coulombs. The coulombs cancel out. Boom. You get newtons. Boom. You're off to the races. Now, after you get that, then you can calculate the acceleration, because acceleration is force divided by mass. Okay? So that acceleration is going to be a pretty big number. So that acceleration is going to be like 10 to the 14th meters per second squared. Okay? Pretty big acceleration. Okay? Now, the next thing, and this is going to be important when you look at what's going to happen on 60B. So on 60B, a proton is shot from the negative disk towards the positive disk. Okay? Now, this is huge that you think this through. You have to, I cannot emphasize this enough. So when you get to a problem like this, and you're going to have like this on the test, I promise you. So a proton is shot from the negative disk towards the positive. What speed must the proton have to just barely reach the positive disk? Okay? So because of the fact that it's a proton, and it's going to be shot from the positive disk towards, excuse me, shot from the negative towards the positive, right? Yeah, from the negative.
So it slows down.
So here's the story. So here's this proton. You're going to shoot it this way. So the first thing you have to decide, if I shoot it from the negative to the positive, is this thing going to slow down or speed up as it goes across? It's going to slow down because it doesn't want to leave the negative, and then it's being repulsed by the positive. So in that situation, that's a similar type of idea to me throwing this ball up in the air. So if I know the height of the ceiling, and I know the acceleration, I want to know, hey, how fast do I have to throw this thing so that it would just basically make it to the height of the ceiling? Do you know time?
No.
So what are you going to use? That equation. Okay? So you're going to go v squared equals v naught squared plus 2AD. You're going to know the acceleration. Now, what are you searching for? The final velocity or the initial velocity?
V naught.
Because you know v, which is going to be 0. You don't know v naught. So that should be something times 10 to the 5th. Okay? Something times 10 to the 5th. If you hand in the test tomorrow and you haven't done something like that, you have missed the point.
Wait.
What?
So on the beginning of number 60, whenever you're doing that, the
Q over epsilon naught A.
Yeah, what charge do you use there?
That's going to be whatever the plates are charged to.
So they're both going to be charged evenly?
Yeah, they have to be charged equally. You
Okay.
can't charge one plate more than the other.
Yeah.
They have to be.
'Cause-
And I've got to give you that number.
okay.
So I'll say, hey, I crank the handle, I charge the plates to
So they
20
both are charged.
nanocoulombs, whatever.
Okay.
Okay? Yeah, I've got to give you that number.
Okay.
On 61, because it used to be before we had like flat screens and plasma televisions, they used to use these big tubes, and these were literally acting, and these were back when TVs were like massive, okay? I mean, literally, TVs used to be huge. I mean, you would build entertainment centers like around the television, like massive, like they were like this big and about this deep. What primarily took up a lot of that depth was literally, it acted like an electron gun in the back of the screen. And so what it would do is that here was your television screen, and it would shoot these beams of electrons at the screen. And when the electrons would hit that material, they would cause that screen to emit light. So basically, you had a phosphorescent screen, you'd shoot them with electrons, the electrons would run into this material on the screen, those electrons would get excited, they would jump, they would come back down, they would emit light, you can watch television, okay? That was the old way that they used to do these things. And they were energy hogs because of the fact that they would get hot and you'd have all these tubes and literally, like, in that style of television, you could not produce a television screen this big, okay, with those old style because of the fact that you just
Would it
couldn't.
just be like the length of the room backwards
Yeah.
or something?
Yeah, it would just be absolutely massive. I remember this is when I started teaching this one. Well, they took them out, but there used to be like two brackets. There were two holes in the ceilings, one on each side, and even that was like in '96, and we thought we were cutting edge because the idea being is that I was actually going to put two televisions, one on each side, but even then, this is like in '96. The depth, they had to be so far away from the wall because those televisions were about 2 feet deep, because that's how they would project, they would excite the electrons and shoot those on the screen. So there used to be, if you were in my room, even up to last year, there were two holes in the ceilings, because they were going to hang brackets, they were going to hang the televisions, so then you could watch, like, your side would watch that side, and they never got them to work, but that was the idea. Okay, so on 61, and that's what, so just kind of give you a little bit of perspective on what's happening on 61. So, accelerates electrons. I'm telling you tomorrow, when you get these questions like this, the first thing you need to decide and figure out, are these talking about electrons or are they talking about protons? Because they're two completely different things. So even if you go back to this problem, if I had shot an electron from the negative side to the positive side,
Speed up.
what would that do?
Speed up.
That would speed up, okay? That would speed up. And then the only thing I could ask you to do there would be to calculate the final velocity, okay? Because that would be like me throwing this ball down, and it's like, well, it's never going to stop. It's just going to keep speeding up.
Could you do like the time to get to the other side too or something?
Yes, you could, but I'd have to give you that, which we'll talk about. Okay, so anyway, so on 61, you know the distance, you can calculate the force, so that force on number 61 should be something times 10 to the negative 14th, and then from there you can go E equals F over Q, and so that's going to be that step-by-step process. And because you know the mass and you know the acceleration, you're going to use that equation, you're going to find the force, and then you can go from there. On 62, I promise you, there's going to be one like 62 on the test. You mark my words. So now, as Morella pointed out, this is a 45-degree angle. So if you know the gravitational side here, what else do you know?
You know the
Then you also know what the FE is. Okay, so you really don't need to do, you have a 45-degree angle, but you really don't need to use that because it's a 45-degree angle. So once you know one side, you automatically know what the other side is. let me give you a hint, tomorrow is not gonna be a 45-degree angle.
Oh.
I'm just telling you.
60.
What's that
You can give us
answer?
some
I don't
weird
know.
angle, aren't you?
What's that answer in like?
Anyway, so your answer to 62 in nanocoulombs should be somewhere between 5 and 10.
That's just a really big one. Like,
I don't think that.
you
Not
know.
really.
No, it's just funny because it's like, oh, between 5 and 10, there's a lot of room for interpretation there.
Oh, yeah.
Oh, yeah.
Infinite, if you think about it.
Yeah.
You just wrote it down.
Yeah, but that's not.
Okay, now let's talk about the spring problem. So you need to work the spring problem in two different ways. So here's the spring. You're going to attach known weight to it. It has an unstretched length of 4 centimeters, which is about like yay, not a very big spring. And you're going to hook it up, and it's going to stretch down to 5 centimeters. So the first thing you need to do is F equals KX. Okay? First thing you need to do. You know the force. Now, this X, are you going to use, you have 3 options for your X to find this value of K. Are you going to use the 4 centimeters? Are you going to use the 5 centimeters? Are you going to use 1 centimeter? Why?
Because that's the distance that it's stretched.
That's how far it's going to get stretched. So your spring constant should be around 1, because if that's wrong, everything's going to go wrong. Now, then we're going to take that spring, and we're going to lay it horizontally, and we're going to put 2 charged particles on each side. Okay? So this is going to stretch. So what do you know about the charges? Are they opposite or are they the same?
I mean, same.
Opposite.
That is the same. Same.
I don't know.
They're the same. They're the same.
Yeah, they're
Yeah, because if they were opposite charge, what
They're
would they
going
do?
opposite
They would
ways.
compress the spring.
Come on, same.
Okay?
Yeah.
They'd compress the spring,
How about
right?
Yes.
I'm looking in the back like, this half of the room is like kind of like in this dark clothing kind of mood, and then this part of this room is kind of
That's like a
festive.
color scheme.
It is, it's just like,
crazy.
it's just
That is
like there was this dividing line,
I know.
you
It's like
know?
we're in our world, Fisher's in his own world.
Yeah, we'll keep,
No,
we'll
they
keep
kind of
it.
like.
No, they got
bright
color.
pinks, little.
Okay.
Pink and then just plain white.
Now, here's what you gotta do.
Like black and blue and red.
Yeah, what the-
You have 2 forces involved, and they're gonna equal each other. So the force to stretch the spring is gonna equal the electrostatic repulsive force, KQ1, Q2 over D squared. Are the 2 K's the same, and can we just cancel them out?
No, they're not the same.
They are not the same.
They are not the same.
Not the same.
They are so not the same. Now, here's the question. To figure out how far it's going to stretch, what do you use for X?
For which one?
Distance of the length.
To figure out how far it's going to stretch.
They tell you, I thought.
Yeah, don't they give
They
you?
told it to you. Yeah,
No,
but
no.
you take that minus the, what's it called one?
When now we're on. This is
Yeah.
when we put these on opposite ends.
Yeah, so you take the,
It says this causes the
Unstretched.
spring to stretch to a length of 4.5 centimeters. So do I put the four?
No.
Do I put in that as 4.5 centimeters,
you do the
1/2
difference.
or do I put in a half a centimeter?
Half a
Half a
centimeter.
centimeter.
Half a centimeter, because that's how far that's going to stretch.
Yeah.
So this has to be that half a centimeter. Now, over here, what do you use for that distance?
4.5.
Why?
Because that's the distance between them.
That's the distance between the charged particles. So if all goes well on the charge, and notice I tell you I want this in nanocoulombs, okay? The charge, I'll narrow it down a little bit, should be, not really, it should be between 30 and 35 nanocoulombs.
30 and 35.
Between 30 and 35. Okay? Look for a spring problem on the test. Jackson.
It's basically this whole assignment.
What'd you say the answer was between
This is
62?
the test.
On which one?
62.
Yeah, do
In
we have to turn this
nanocoulombs,
in?
between 5 and 10.
Oh, yeah, can we keep this assignment?
Yeah, if you wanna hold on
Yeah,
to
can
this
we to
assignment,
study to do this?
if you wanna hold on to this assignment and hand it in tomorrow, you can,
Alright,
okay?
How many?
That's up to you.
30 and 35. 30.
Are we gonna go over the worksheet too?
Yeah?
Very nice.
Yeah. Tell us
Okay.
what letters it's between.
0.045.
Specifically.
The letters it's between.
You need the book.
Son, I need the book.
No, I'm done for book.
Can I grab that?
So like,
Are we just reviewing? Are we just reviewing today?
Yeah.
What do we always do before test?
No, we just sit here and
Are you good?
please. Oh, please.
That's a good feeling, though.
No, it's not.
No?
When they pick.
how many pages is this? Is this a long
That's
test?
your charger?
Well, it is just because a lot of these are like the diagrams are pretty big. So it's about the same number of questions, but like one multiple choice question is 1 page.
Do we have to draw a diagram?
Not like exact.
Yeah,
Okay.
30.
Louis,
Did you find a charger in your classroom yesterday? Or did any kind,
We weren't here yet.
charitable soul?
We weren't here yet.
Samaritan.
But, people were.
no.
Did you? Man got his charger stolen.
I left my charger here, back there.
Oh, is that my fault, Luke? You're blaming on me now?
The charger
So-
was, the calculator was.
No, it was not. You left it.
Bring back this beef.
Yeah.
Wait, so what did you lose?
It was, I left the charger back there, I wanted the wall outlet.
Just the cord?
No, the block too.
How'd
The
you
Well, you see, this
Wait,
is a
wait,
presiding
wait.
incident.
Hold on.
Like, this has happened before.
How do you leave just the charger?
Yeah, man,
Louis,
found
I
that.
don't
That means
think-
something was charged.
Okay,
You had to
number
go
one,
grab it.
no one would have any advantage to take the charger. And no
Is
one
it a
was
fast
really back
charger?
there.
Or
Yeah,
is it a
this
normal?
is super good.
Oh, that's
okay,
fine.
yeah,
That's
it was a good charger.
It's a fast charger. So
Trust me.
the circle block ones?
Yeah, I would snack those.
People always have a reason.
I would snack.
Okay.
If I saw a Chromebook charger in this room, it's not. No one has them.
I have
Do you have a
mine.
Chromebook
They're like-
charger?
I have
Does anyone
two.
have a Chromebook charger?
It's like an
Okay.
endangered species.
I do.
Chromebook charger.
Or the
Yeah,
calculator.
It's a rare
Calculator.
I thought you were just talking about your basic run-of-the-mill, hey, that's issued to everyone.
No, like.
I've left my AirPods.
Okay, I have not seen one.
I've left them.
Okay.
Thank
This
you.
is like 18 times.
I'll keep my eye out for it.
Ah,
They can just
Oh my
resell
god,
it.
I also
Okay.
got
What's gonna check them out in China and you're gonna go chase them after?
Someone at Maysouth is gonna sell.
Oh, I didn't circle though. I got it on my paper though.
I was like, really?
Okay.
No, I'm saying like they don't sell it to like some random spot. for
Yesterday
cheaper,
was a
bro. So
struggle,
you're
that is
gonna
for
go
sure.
pull up
Pawn
to-
But I pushed through, you know?
Get your AirPods back.
Yeah.
Yo, bro. My AirPods are in there.
Ah, you're in the wrong spot, dude.
No, bro. Like,
Get out of
if they sell it, you're not gonna go after it.
Yeah, I'm gonna
Would
go
you?
after it,
You're
bro.
gonna drive. You're
Yes,
gonna
I
drive.
am, bro.
You're gonna drive to wherever they're at.
pivot over.
Yeah,
Flip the
Did I
car,
tell you
crack
about
your
my
car.
Walmart?
Okay, so let's talk about that first big question. And I promise you, there's gonna be something, this is so important that you get this idea of fields. So, for now, let's leave out the top charge, okay? Don't worry about the top charge, pretend that that's not there. Boom, gone. Okay? So, I've got a positive Q, and then over here I have a positive 2Q. So let's start with this idea. Is there a point in between those charges where the net electric field would go to zero?
Yeah. Yes.
Alright, time out.
Louis?
No way. It was in his back.
I went 2 days with a dead phone just for finding my bag.
You don't have another
How do
one?
you not have a single other Apple charger? But this, there's so many things wrong with this movie. It's bad.
Just keep going. It's fine.
You lack
Left your phone dead.
the capacity to create charge.
There's
Yeah.
no way.
My cards.
There's
Is
no way you
that
have another
what it
Apple
was,
charger.
Louis?
I just need to get a
There's
wall.
no way you couldn't even
I'm
ask
gonna buy
someone
a
for another
pouch.
Apple charger.
Well, no,
Just let your phone
Yeah.
be.
Go with
That is
that.
Nobody in your house has
You
that
can
shit?
watch,
No, they don't.
have him
That's
watch
what
me.
you
Okay,
spend
anyway,
24
alright, back to our
hours.
story. Back to our story.
I mean, it's not bad. I would.
So, so you have a positive 2Q at distance R and a positive Q on the outside. So is the point where the net electric field, not force, field, is going to be 0, is that to the left of the origin or to the right of the origin? Why?
Because the electric field is stronger than from the 2Q.
Okay?
Yeah.
So, how do you calculate the value of that electric field?
KQ over D squared.
KQ over.
D squared.
Or R squared.
So, if this distance here, let's just say, is 2 meters, let's just say.
Let's say.
So, if you let the distance from 2Q be R, what's going to be left over?
R minus 1. I don't know.
Wait, can you
Oh,
repeat?
2 minus R.
Yeah, 2 minus R, right? So if you think the distance to where the electric field is going to go to 0 is going to be R, this distance over here is going to be
2 minus R.
2 meters minus R. Cool with that? Like the Lagrange point with the moon, balancing things out, right? So algebraically, how would you set it up? So if you're defining this being Q, so you can have KQ over what?
R squared.
Oh,
No, no,
that's
no.
Q.
Sorry.
That'd be 2 minus R.
That'd be 2 minus R squared.
Equals
And that had to equal
K 2Q over
K times 2Q over
R squared.
R squared.
R.
K is going to cancel out, right?
Yep.
Yeah.
Q.
What about the Q's?
They cancel.
Q's cancel.
The Q's are canceled.
Yeah.
So you're going to have 2 times 2 minus R squared equals
Equals R squared.
R squared. Then it turns into an algebra problem.
Yeah.
Expand the binomial, boom, there you go. Okay? Look for that idea on a test near you. So let's go back to this
Is that what
problem.
you guys did?
Yeah, I have to do that.
Oh, I
No, you
didn't.
don't.
Oh, okay. I was like,
No, I'm just saying that's something I could do on the test.
You could do, or you
I
want
could
to
do.
do.
Maybe
Off the
yes,
brag
maybe
now,
no.
Mr. Burkamp. We can do it too.
Huh? You
Off
can't
the
keep
brag.
track of your charger, seriously.
I'll take that. Oh, I'll take that. I deserve it.
Speaking of charges, okay,
oh my.
Got you.
That was gonna
Now.
be.
so here's the origin. What's the direction of the field
Not turning this is on.
at the origin created by that positive Q? This is something you have to do without hesitation.
Direction of the field.
Vitor,
That way.
why?
Because if you put a positive
Yeah.
charge there, it would repel.
Okay? So from Q, that's going to direct a field in this direction, right?
Yeah.
Okay? Because this is a positive charge. That's going to push it in that direction, right?
Yeah.
Okay. Now, pretend that that doesn't exist. Here I have 2Q.
Yep.
That's going to go to the
Left.
left, because a positive test charge is going to get... Now, which one's going to be bigger?
To the left.
So, this is going to be from the 2Q. So what's the direction of the net electric field caused by the Q and 2Q?
Negative
One
E.
Q.
Going to the left, right? It's a tug of war being pushed.
1 Q. Or 1 E.
So I know that E, that net electric field of the origin, is going to be pointing to the left. Cool with that? Okay.
Yeah.
So you could do KQ over R squared, and then you're going to have K2Q over R squared, and the difference between those two is going to be your net electric field, right? Cool with that. One's going in one direction, one's going in the other.
Yep.
Cool with that.
No, I didn't know.
What if they were both, what if this had been negative 2Q?
And it
They didn't
would've
go
been
that way.
They would both be going
That way.
that
Three
direction.
cubes. Oh, I need really cool.
Do you have enough information to calculate the force at the origin? Do you have enough information?
Not to calculate the force, no.
Why not, Louis?
Because you don't have any numbers. It's just
No charges.
I mean, you could do it with like.
You don't have the charge in the middle.
I don't have the charge in the middle. Okay? Because to calculate the charge in the middle, what would you have to have?
Q.
You'd have to have the charge at the origin.
Yes.
Could I calculate the force between the Q and the 2Q?
Yes.
Yes.
That I could do, right?
Yep.
So now, would that force cause them to be repelled or attracted?
Repel.
Why?
Because they're the same charge.
Now, I would actually have to give you the value of Q. 10 nanocoulombs, 5 nanocoulombs, something like that. I would actually have to give you the distance between them, right? So that would make them be repelled. Cool with that. Now, back to the central question here. Now we have a charge up here of negative Q. So don't worry about the Q and the 2Q. With that negative Q, what's that going to do at the origin? Which direction is that going to go? Up. So this is going to be pointing up, right? So I've got a component of my electric field pointing up. What else do I have?
component pointing up.
A component pointing to the,
Left.
so what's going to be the direction of my net electric
45
field?
degree angle.
Somewhere up and to the left. True?
Yes.
Somewhere like that. Good with that? Okay. So with all of that said, then you want to determine the value of the magnetic field at that point. So now this is where you're going to use the Pythagorean theorem.
Yes, I did do that.
Okay.
Indeed.
So you're going to have the net electric field created by these two. The net electric field created by that, use the Pythagorean theorem. There you go. And your answer is either B, C, or D.
Wait, so don't use the Pythagorean theorem
Yeah.
if there's like if it's attached to something, kind of thing.
Not,
Because
yeah,
that
there's
would be
nothing really to be gained.
tension.
Yeah.
But like on these, you can
Yeah.
to find a net. Okay.
We're gonna solve.
Off his charger.
When you get to Louis, I'm just so thankful that's happened the day before the test, or I would use this example for you all the time.
What, the charger?
Yeah. I'm not going to let this one go. So here's a conducting sphere.
He's not.
Louis lets his charger inside the conducting sphere. Okay? And it has a negative charge. Okay, the whole key to this is a conducting sphere. Louis,
Yes.
here's your conductor. It's negatively charged. What's that going to do to this sphere around it? You have a negative charge
Oh,
inside of it.
okay. It's gonna start pulling it towards, right?
Okay, what is it?
Sorry. The charge in the middle.
There's a
has
charge in the
a
middle.
Attractive force on the sphere on the outside.
It's negative.
I got it.
A what?
Hold on. Louis.
It sends electrons out.
Louis. Think about what's going to happen to the electrons that make up that
Yeah,
sphere.
they go towards the outside.
They go towards the outside. Okay? So the outside of the sphere is going to become
Negative.
negatively charged, right?
Okay.
Okay?
Yeah.
And the only reason I'm worried about that, because that's what the question is asking for, is about what's going to happen to the
The
field on
outside?
the outside of it.
Oh,
Yes.
sorry. Yeah. Okay.
Is the inside going to feel an attractive force towards the electron?
Yeah.
Yes, very much.
No.
Why?
Because
I don't know.
it's one electron.
It's one electron. It's 1.6 times 10 to the negative 19th coulombs.
1.16.
Are you
Okay?
talking about like the material of it, the shell,
Huh?
the shell itself?
Like, it's like a whole.
Yeah, it would, that, all
So
of
it doesn't
those
feel an attractive force at all.
towards the inside.
Wait, what would happen if you had a big negative charge in there then? Would it just collapse on
If
itself?
you had a big enough
Big
one, but
enough
it would
one?
take, it would be
Just collapse on
be
itself?
absolutely massive.
But you wouldn't be able to get it in there. Would you?
Yeah.
How would you do it if it's a closed sphere?
You'd have to have a wire that ran through it.
It's gonna suck you in with it?
And then hook that up to like a Van de Graaff generator, and then it would dump those excess electrons on there.
Turns into a black hole.
Okay. Universe collapses. Black hole created in physics room at Mays High School. Okay. So, that'd be awkward. All right, so we just established that the outside is negatively charged. So, fish,
Yes.
the outside of this sphere is negatively charged.
Yep.
What's the direction of the electric field?
Inward.
Why?
Because if you put a positive test charge, it's gonna go towards.
Bingo. Positive test charge would be attracted towards that. So therefore, the electric field is pointing inward. Now, if I'd put a proton in the middle,
Away.
It'd be outward.
because if I put a proton in the middle, what are the electrons going to do? So then the inside would become negatively charged, leaving the outside being,
Positive.
and then it would
Ah.
repel. Like that?
Yes.
Okay, that got the chin tap.
Yeah, I was like kind of confused on why I was making the shell, but now I see. Okay, got it.
Okay. I promise you, there's going to be one similar to that on that back side. Okay? So, let me give you a hint on how you start this. So you got negative Q, positive Q, negative Q, negative Q. Okay? Some distance D.
See the pasta you ate? Pasta.
Now, here's the deal. Can you talk, again, I can talk about the field, but I can't talk about the force because I don't know what the charge is that's in there. I can only talk about fields, okay? I can only talk about fields. So, here's the positive test charge. What's going to happen with the two negative Q's on that diagonal?
Cancel out.
Why are they going to cancel out?
They're both the same value.
So a positive test charge here is going to do what? It's going to attract that way, and it's going to, so those
Cancel.
don't care about them, okay? Not part of the story. Now, what about here?
Positive's gonna push it.
It's going to be pushed that way, and it's going to get,
Hold versus
so if I find one value of the electric field, all I have to do is double it, okay? So keep in mind that each of those halves are d over 2. Now, if variables flip you out, okay? If you're going, man, I hate variables, I hate dealing with these, sucks. If I were y'all, I'd let that, if you're gonna put in numbers, why would I let that overall distance be 2 meters?
Instead of dividing it, it'd be 1.
Yeah, it would just be 1 meter, so I'd just have 1 meter by 1 meter.
Yep.
Okay? So if you want to do that, but then that works out, then your hypotenuse is what? The square root of
So,
2, but that's going to get squared, so it just becomes, so keep that in mind. Okay,
which one was? Oh, you can't.
so, good with that one.
Yeah.
Like I said, if you can hold on to that assignment, you can, that's up to you. Okay, so stop that. Problem. So start that back up and kind of give this a speed. So I've got 2 conducting spheres connected by a conducting piece of metal. Okay? And I happen to have a electric field sensor. Just let me set that. So I charged the balloon, and we're very much reading a negative value. So when I bring it closer, what happens to the strength of the electric field? It gets greater, I move it away, decreases. Okay? Now, what I'm gonna do, this is two conducting spheres connected by a connecting rod in between. That's also conducting, okay? So I'm gonna put my sensor over here, reset that. And so that is, go to a sensitive. So that is neutral at this point. Now, as soon as I bring this balloon near, you'll notice that it starts to light up and go negative. Why?
You're all moving to
Okay,
the
since that's negative,
electrons-
Because this is negatively charged, right? Very negatively
you
charged.
induce a
Negative.
positive charge on the right one, and then that
And then
induces-
all the
negative ones all go over
electrons
the
are
other
pushed
side.
over the.
So, as I bring this negatively charged balloon near, okay, the electrons are being pushed over. So, right now, if I move this away, come on,
Come on, man.
Open the door.
goes back to being neutral. Now,
Elbow washer.
what would I want, if I want two spheres that are equally charged but oppositely charged, same magnitude but oppositely charged, what's the sequence? With the balloon and those spheres.
What's the sequence of what?
What'd you say, Jackson?
You put them together, you touch the balloon to them, and then you pull the balloon away and look at them.
Okay, so if I bring this balloon near here, what's going to be the charge on the one closest?
Positive.
Positive. One on the right's going to be?
Negative.
So if I take this,
Disconnect
now,
them, and now it's-
Disconnect them.
if I, because they're connected, or if they're touching, same idea, because that's allowing that to happen. So if I move this here, that should be,
Negative.
Negative.
and this one should be.
Positive.
So now if I do this and separate them, I should now have two charged spheres, okay? And hopefully that works. And it worked the opposite.
So did
They
it
both
attract-
ended up in,
What?
well, I think what happened is that when I grabbed the middle, I sucked the electrons off.
Physics book.
Okay, but now, here's the difference. What if these are touching? These are touching. And I bring in a negatively charged balloon and I actually touch it
They
to
share.
them.
They share.
Then they're both, everything's gonna be negatively charged, so I'm gonna distribute this negative charge over all of it. So if that's the case, everything should be
Negative.
negatively charged. And
Man, it's awesome.
They're both positive.
they're both positively charged.
Oh.
Okay, hold on,
Rub the
Physics
balloon
works.
again.
hold on.
Give it
It's a
over.
low gravity way too.
We broke fingers. Oh, I had a cheeky windows roll.
Cheeky man.
That is a pleasant.
Yeah.
Cheeky.
We had windows
No way.
You had a cheeky
Is
one.
Nando's sauce good?
If I do
Really?
it fast enough.
Oh, I actually want to try it.
Still positive.
Oh, there it goes, there it goes negative.
So big.
general manager.
Oh, there it was negative. It was negative, started very briefly. Okay. I understand that part. Let me see.
It's like a British version of Chick-fil-A. But like way better.
The balloon has the electrons, right?
No,
It's not
no, it's not. I
biased.
think it's better. Because it's not,
It's not as fried.
It's like chicken wings.
Shares
Yeah,
the
it's like
electrons over
grilled.
to those spheres, and it keeps protons.
But that's good sauce.
Pull the balloon away.
Does it like taste like Chick-fil-A? Or what's the
No,
taste?
that's
What's the
It's like,
taste?
It's the
Cane's?
vinegar, I guess. No.
Vinegar?
It is.
I don't know.
It's like, I don't know, Northern African.
Don't worry about that.
I don't even know what that means, bro.
Like Morocco and.
Yeah,
I've never been to
Sauce.
Morocco.
So it's just a spicy one?
You don't know where it is?
Bro, just compare like, what is it, like barbecue mixed with,
No, it's not, it's like.
Is it like
It's
spicy
okay,
or?
it's like hot wings where it's like kind of vinegary,
Yeah.
but it's so hard to explain.
It's just good.
Yeah, it's just good. It's kind of vinegary.
Why don't you bring some for us?
Fine.
Alright, tomorrow.
Fine.
Or, no, Friday, if we have school.
Friday.
Test tomorrow.
it's gonna snow Friday.
No, it's not.
Just bring-
It might snow.
We should have a Nando's day.
Don't jinx it.
He's jinxing it.
You are all jinxing it. Just
Yeah.
don't talk about it.
Oh gosh. We should have snow day tomorrow, honestly. And then like the test.
And then snow day Friday as well.
Wait, so Mr. Bergkamp,
What?
when you touch the balloon, does the balloon lose its negative charge?
Yeah, because it's gonna distribute those electrons over.
Why does it do that? Why does it go from the
Does it go to positive?
Because it's just at a lower, it's just at a higher state of
Wait,
equilibrium.
so you just touch one of
I'm
them
trying
and
to
just
fix
make
the
that
camera
one
so I
negatively
can-
charged?
Yes.
Okay.
There we go.
Okay. So, you have an electron being shot between two plates. One's negatively charged, one's positively charged. The distance across the plates is 12 centimeters. The electric field in between them is 1.8 times 10 to the 4th newtons per coulomb. The electron comes in at 5.0 times 10 to the 7th meters per second. I want to know how far is it deflected and in which direction is it deflected.
It's an electron.
Go.
Oh my
No?
goodness.
Wait, this isn't one of these problems? This is another?
No, this is different.
What do you mean?
This is
This is towards the negative up, or do
Looks a
we
little
just say
difficult.
towards whichever one?
Yeah, it's either going to be deflected up or deflected down.
Wait, we have to know the
And up is that way?
magnitude.
I want to know how far it's going to get deflected.
You put what into it?
And either is it going to be deflected up or is it deflected down?
Does it start in the middle?
Yes.
And it's an electron? Oh, wait.
It's an electron.
Okay.
That's actually how much is it deflected?
What happens in the X stays in the X. What happens in the Y stays in the Y.
Wait,
Hmm.
wait, hold on.
What's the two plates? Those like this?
Yeah.
Where the
Where's the electron coming
You
from?
said that's the electric
Right.
The
field?
electron's being shot across.
The electric field is.
Where?
So-
10 times 10 to the
The electron is coming in here, and it's going to travel a horizontal distance of 12 centimeters. Okay? And it's moving at 5.0 times 10 to the 7th meters per second. So the electron's going to come in like this.
Oh, so it travels 12 centimeters?
It's going to travel a horizontal distance of 12 centimeters. Okay? So what I want to know is how far and in which direction is it going to get deflected.
It's like the OG.
It's like a projectile motion problem on steroids.
I feel like we've had a problem like this.
You have had a problem
Okay,
like this.
Yeah.
We don't get to know where it starts, like in between those?
Doesn't matter. Not part of the story.
I don't like this.
Sorry.
What do you mean by deflected?
Like, which way it's going?
What is the E?
Like how far up or down?
Yes, how far up or down it's gonna go from the path that it would take if there was no
Oh, you're
electric.
saying it doesn't ever hit the thing?
No.
Oh, okay.
Wait, do we need to know how fast it's going?
After 12 centimeters, does it stop? Or is it still going?
That's just the end point.
Don't, not, y'all are getting hung up on this, do not.
Alright.
This is good.
Is the electric field is positive going that way, right? No, the electric field.
The electric field, okay, let's start with the direction of the electric
It's
field.
going,
What's the direction of the electric field?
Going
Up or down?
oh, it's up or down?
Vitor is all excited about pointing up,
It's not up.
and Pop is pointing down.
Oh yeah, I forgot there's little thingies there.
It's down.
It's
bro.
up.
What's the direction of the electric field?
Oh.
Up or down?
Okay, I forgot.
Why?
Because you
Because
use a
it's
proton.
negative up there.
That's right. So if I released a positive test charge here, which direction would it go? Up. So the electric field is pointing up for a positive test charge. But when
When
this
you play
electron
first,
comes
that's what
through,
I
what's
did.
it gonna do?
Down.
It's gonna go down because it's a negatively charged particle.
Right.
How much is it?
Ah.
The whole electric
How
field.
much is it?
Counting the positive and negative one.
What do you mean? Hold on, I didn't hear what you said.
That's the value of the whole electric field
Yes.
going through there, both of them, so you don't need to.
No.
Oh, what
that's-
happens in the X stays in, okay.
Yeah, that is the value of the electric field.
Okay.
Mm,
Easy. It's an electron?
Yeah, boy.
1.6.
So on those
0.0.
free response questions that I gave out, I will scan those and send you those, email you those answers.
What's the math? Did you get the math?
So what's the first thing you can find?
Force.
Using what?
Effect.
Effect.
Don't. Yeah, forced. Well, I did force, right?
1.6 times 10 to the 19th.
What is how much is it deflected mean? Like, what does that mean?
How far does it move from the straight line path that it would take
Oh,
So like how much it goes
if there
up?
was no electric field?
oh.
So basically, how far is it gonna, what's the vertical distance it's gonna move up or down
It's 10
from the straight line path that it would take?
Oh.
3
Once you get the force, then what can you find?
Acceleration.
You can find the acceleration, because force equals mass times
Is
acceleration.
that going to be a vertical acceleration?
Because are there any forces acting in the horizontal direction?
No.
No, because the electric field is pointing up, right?
Oh, so
But the
that's-
path is going to be, because it's an electron, the path is going to be downward.
So then, is that our x component then?
That's the x component
And
of the
then y
velocity.
component will be your acceleration. You can find your velocity. Yes? No?
Let me give you a hint. I take this ball and I throw it completely horizontal.
Velocity is constant horizontally.
Oh! My velocity is constant horizontally. Do you know how far it goes horizontal with a constant horizontal
You
velocity?
can solve for time.
You can figure out how long it takes to travel that distance. Because you know how fast it's going, 5.0 times 10 to the 7th meters per second. True?
Yeah.
What are you going to do with the 12 centimeters?
Use that as distance.
Is your time to travel that going to be a really big number or a really small number?
All those.
Going to tiny number. It's not going to take very long at all.
Alright. We got
So
it.
then,
We got it.
so here's going to be your steps. Find the value of the force. Force divided by mass equals your acceleration. Then you go distance equals 1/2 AT squared plus V naught time. What happens in the x stays in the x. So what's your initial vertical velocity? 0. This part drops out. True? How are you going to get your time?
Square root of 2x over a.
Well, to get your time, you're just going to use distance equals velocity times time. Because the horizontal velocity is a fixed value. Your distance is a fixed value. Take that time, plug that in there. I will email you the answers to those FRQ questions.
What's that? Was that 10 to the...
I don't know. I just made up the problem.
Hold on.
You don't know the answer?
No.
Is this on the test?
Yeah. Oh, I promise you. If you hand in the test tomorrow and you haven't done something like that, you have done something wrong.
Is it 10 to the 7th meters per second?
No.